Hey guys, so yesterday we talked about chemical bonding, the different types there are, two specific ones more importantly than anything, the ionic and the covalent, and then we focused just mostly on ionic. So let me just do a real quick review and then we'll get started on covalent. So if you'll recall, yesterday we talked about this imaginary line on the periodic table, right? And it separates your metals from your nonmetals, like we already know. Metals, nonmetals, hydrogen being a nonmetal on the wrong side of the periodic table. Okay, so if I put a marker on Rb and Cl, because that's a metal coming together with a nonmetal, that means it is ionic. And if I have two nonmetals coming together, like N and Cl, that means that it's covalent. So if we wanted to just really quick review, we talk about Na and Cl for an ionic bond, a metal and a nonmetal. We would look at sodium, which is in the first column, which means it has one valence electron. So we would put Na with one dot. And then if we had chlorine, we look at chlorine, we go to the top, group 17, hide the 1, which means that that's really just 7 valence electrons. So we would do Cl with 7, 1, 2, 3, 4, 5, 6, 7. And as we said yesterday, metals always give, nonmetals always take. So Na would give its electron to chlorine, and if it does that, now that means that chlorine has 1, 2, 3, 4, 5, 6, 7, 8, and sodium would be lost with that 1 and be happy because now both of them are noble gases, no electrons in its outermost extra shell, which means now it's full with 8, and chlorine now has its 8. All right, and then if we were to write that formula, because there's one Na and one Cl, that's like saying Na1 Cl1, or like in math, we all know that's really just NaCl. Reduce 1 to 1. If it's a 1, you don't need to write the 1, it's understood. And then we just name it sodium. And then for chlorine, that's going to be chlorine. But as we were talked about yesterday, change the ending from "ine" to "ide." So it's really sodium chloride. All right, and I keep crossing it out like that. Really, what I'm going to expect you to be able to do is just write sodium chloride. So you just say sodium chloride, you're done. Now what happens if instead of having the symbols and you write the name, what happens if I gave you the name? So for example, what happens if I gave you, let's say, lithium sulfide? All right, so we already know that the first element is always the first name. Okay, so you would look up, and we all know that lithium is Li as the symbol. Sulfide, remember we changed the ending to IDE, which means it has to be on the periodic table somewhere. And what does sulfide sound like? Hopefully you also know that it has to be a nonmetal. The element in the second position must be a nonmetal. So we're talking about one of these over here, or hydrogen, and hydrogen does not sound like sulfide. So hopefully you would think that means sulfur. So we would write S. Now, here's the problem. We have lithium and we have sulfur. Okay, you're not done. That's not the formula. LiS is not done. You just have the bare bones. Now we have to go back, and because it's an ionic equation, or sorry, ionic bond, we need to look for the ions, the charges. So, well, we know that lithium is in the first column. It has a +1 charge. So lithium is a +1. We look for sulfur. Sulfur is in oxygen's family. It's much more electronegative, only wants 2 more electrons, so it's going to be a -2 charge. Now, if you'll recall from yesterday when I showed you the crisscross method, this is what's going to happen again. If you'll notice, a +1 and a -2 does not equal 0. They do not cancel each other out. Either they both have to be +1 or they both have to be plus or minus, sorry. They both have to be plus or minus 1, or they both have to be plus or minus 2. This way, they do not equal 0. So we have to crisscross our numbers, not the charges, just the numbers, to cancel everybody out. And I'll show you what that means, if you'll recall. Okay, and then a 1. We just drop them down. Okay, crisscross. Now, what that really means, like we said yesterday, is that you have 1 Li, 2 Lis for every 1 S. And as we said yesterday, if you'll remember, lithium has 1 dot, sulfur has 6, group 16, 6 dots, group 1, 1 dot, and for sulfur, 1, 2, 3, 4, 5, 6, it needs 2 more. So there's 7, there's 8. So 1, 2, 3, 4, 5, 6, 7, 8. Sulfur is content. Each lithium gives 1 away, so they are good. So that is why our equation in the end really is Li2S. Metals always give, non-metals always take. Okay, so let's try one more just to verify. Okay, ideally you shouldn't have to rewrite all of this every time. Just checking the charges should work and be suffice, unless I tell you to draw the bond. Okay, so let's try. How about, let's do calcium and phosphorus. So the name would be calcium phosphide. The IDE ending, of course, because it's the second element. Second element is always IDE ending. All right, now, so I showed you that it's Ca, and I showed you that it was P. So if we look on here, we're going to look for calcium. Calcium is a +2 charge. So I'm going to write a +2. And P is a -3. So P with a -3. All right. So again, this does not equal 0. They're not both plus and -2, and they're not both -3 and +3. So because of that, we have to crisscross the charges, or the numbers. So the 3 comes down here, the 2 comes down here. And now for every 3 calciums with a +2 charge, that cancels out 2 phosphorus with a -3 charge. Because notice 3 plus 2's, +2, +2, +2, is equal to 2 -3's. -3, -3. That equals a +6 and a -6, which then in the end equals 0. The whole purpose of what you're trying to do. So there's your formula for calcium phosphide. When it's all said and done, it should be written Ca3P2. Which now brings us to the new material for the day. I said covalent compounds, we're going to skip another day. We're going to wait and do that tomorrow. We're doing transitional ionic compounds. So if you can imagine the word transitional, it should hopefully sound like transition metals. So if I look at my periodic table, we are now talking about all of these guys in the middle. And it could include these at the bottom, but I'm going to be real honest with you. If you got one of these at the bottom, it'd be very, very, very rare. So we're focusing on these elements and even some of these guys underneath the little staircase. All right, I know that these are our transition metals, like it says here. However, every once in a while, you'll get some of these as well, as only because once you get under the staircase, things get a little foggy. So let's do a couple examples of these. This is going to be one new thing. If you don't know your Roman numerals, you're going to be into a little bit of trouble, so we need to make sure that you understand what Roman numerals are. Okay, so really quickly, with transitional ionic compounds. Transitional again, because they're in the valley. Ionic, because they are a metal and a non-metal. All right, so our Roman numerals are, if you'll recall, Roman, okay, we have 1, 2, 3, 4, and 5, right? 1 less than 5, 5. So then that means that 6 would look like 5 plus 1. 5 plus 2 would be 7. And then, of course, you get to 8, which is V, I. And then IX is 9. And then X is 10. So hopefully you remember these. If you don't, hopefully you'll have this written down somewhere so that you don't forget. All right, and because these are going to be used for all of our transitional ionic compounds, or some people just call them transition compounds. Okay, I'm going to call them transitional ionics because they're still ionic and they're because they're in the valley. And I called this the valley because it's between the mountains, if you will. So this is my valley. All right, so here's an example. Let's do an element that you're used to. How about Fe? And if we write Fe, that's going to be Fe. And then I'm going to write, let's do Br. Okay, Br. Okay. Now here's the only thing that we don't have for our compound. We don't have any numbers down here. So I'm going to write some numbers and then it'll hopefully make sense in a second when we do the reverse crisscross. So let's do a 3 here. And then it'll make sense here in a second why I did that. All right. If we were to name this normally like we did before, this would just be iron bromide, right? We would say iron and then we would say bromide. Iron bromine, change the ending to IDE. In the issue of transitional ionics, the problem is now these guys are in the valley. If you'll notice, none of them have charges. Everybody else does on the periodic table. No charges down here in the valley. There's only 3 elements that have the charge and stays the same all the time. The first element that stays the same all the time is zinc. And I don't know if you can see it on my periodic table. It's kind of hard to see. But it says that zinc is always a +2. All right, and if you can see that. So it's always a +2. Silver is always a +1, no matter what. And then aluminum is always a +3. We already knew that because it's in the group 13, so it's always a +3. But if you'll notice, look at some of my other elements on my periodic table. For example, palladium, or palladium, however you pronounce it. Okay, it's a +4 and a +2. Or mercury, a +2 and a +1. Or cobalt, a +3 and a +2. Notice they're all pluses, which is the right thing because remember they all give electrons. It causes them to be positives. But a lot of these elements have more than one oxidation state, which is why they're called the transition elements. They transition from one charge to another. So with that being said, if we look at iron in our thing, in our little compound here, okay, it says FeBr3. So in parentheses, we need to have our Roman numeral, our charge. So if we do this, remember, where did this 3 come from? There's no little 3 on bromine on our periodic table. There's no little 3. It doesn't say Br3. It just says Br. So that 3 is an indication that it came from Fe's charge. And then we already know that Br is a -1. We'll always know the charge of the nonmetal. Always. So Fe is our understood 1. And remember, if the charges didn't equal 0, they crisscross. So there's my 1. That's where that 3 came from. Which now means that that 3 right there goes here. That's our Roman numeral 3. So the name for this compound is iron 3 bromide. Okay? Which is slightly different from FeBr2. So how would you name that one? Yes, iron again, put our Roman numerals, because we know we're going to need some Roman numerals because it's in the valley. Iron is in that area of the transitions. And we still have bromide. As you were thinking and already saying, well, that 2 came from here, and the understood 1 came from there. So this is now iron 2 bromide. And what you'll notice on iron is that iron can have many charges. If I can zoom on this, iron can actually be a +6, a +3, or a +2. Which one you have, you don't know unless you do what we just did and crisscross our charges. Alright, so that's what happens with our transitional ionics. It gets a little funky and a little weird, but as long as you're willing to do like a little bit of a mystery and try to figure out what is the number in the valley or in the parentheses, you'll be able to figure it out. So now we're going to go backwards. That's finding the name from the formula. Let's do the name and then determine the formula, which it will probably be easier now that you know what the Roman numeral stands for. Okay, so I'm going to get rid of these. And we're going to make it a little tricky. Okay, so let's do, how about manganese, which, hint, hint, nudge, nudge, wink, wink, don't make this mistake on a test. If you see Mn, that is not magnesium, that's manganese. Alright, so we're going to do Mn3P7. Alright, and now we need to know our Roman numerals, what they look like, and all that kind of good stuff too. Okay, so as I said, Mn, well, if you look on the periodic table for Mn, that is manganese. He is in the valley down here, so we need to use a Roman numeral. So, manganese. Now, you know he's in the valley. You know you're going to need a Roman numeral. And P is phosphorus. So, phosphide. Not phosphoride, it's phosphide. Okay, now, what's the charge on manganese? Well, again, we already know that P will always be a -3. Always. So use your little hints. If that's a -3, then what's manganese's charge? If you said 7, you're absolutely correct. Which means now you have to put a Roman numeral 7 in here, which 7 looks like that. So it's VII. And done. There's your formula and your name for manganese phosphide. We can do one more, and this one's going to be the trickiest of all. And I won't say anything until we'll see if you guys can figure it out, what's wrong with it. Alright, so I'm going to pause it for a second and I'll start it back up in a sec. Alright, our last example for the day is CrO3. If you look on the periodic table, you'll find Cr, yes, of course, it's in the valley, and oxygen's over here, so it is again transitional ionic. So, Cr, you would look it up and you would say, well, that's chromium. ChROMIUM. And we already know that we're going to have a Roman numeral because it's in the valley. And then O, as we all know, is oxygen. Well, you change that to oxide. Okay, now, what's this charge in the middle? And I'm going to tell you right now, if you say 3, you're wrong. As I said, this is a tricky one. Okay, this would imply, of course, that the 3 came from here. Okay, so you travel it up, and so that would say that this is a +3. But then what would that imply that oxygen's charge is? That would imply that oxygen's charge is a -1. And if you look at the periodic table, oxygen does not have a -1. It has a -2. And like we said before, oxygen, no matter what, always has to be a -2. Always, always, always. Which means, okay, and here's where I said this is going to be tricky. If this is a 2 and the 2 is not here, it's because our numbers were reduced. We have the lowest common multiple down here, or reduced form, however you want to say it from math people. Okay, so if there's a 2 there, then that really means what's 2 times 3? 2 times 3 is 6, which really means that that's a 6 and that your charge up here is actually a plus 6. And in here, you would write a 6 for Vi. And then the actual name is chromium 6 oxide. Okay, I'm really hoping that this is making sense. It's hard to show you guys stuff and not actually be able to ask you questions or say, whoa, stop right there. So for right now, I'm going to stop there. If you have questions, please message me, text me, whatever it's going to be, and we will go over whatever we need to. All right, guys? And remember, don't forget, go to the Brightstorm, or go to Tyler DeWitt, or Khan Academy, Bozeman Science. All these people do phenomenal videos on all this stuff, and do it such a great job compared to what I'm doing. All right, hang in there, don't give up, ask questions.